Alrighty, I think we're set up. We got a couple things to talk about today. I forgot to mention enums from last week for object-oriented programming section, and the first project uses enums as well. It's just a nice way to put a name to something, so we'll take a look at that first, and then we'll come back to recursion. So we've got today and Thursday to talk about recursion. Now, if you were with us last semester, we talked about it briefly. I think we did the Sudoku solver, and we got that working, right? Just took a little bit of extra time. That's the only example we did, right? We didn't do the maze solver. Okay, so we'll do the maze solver. Let me open up a new project. I can do enums right in here. So I'm just going to add to this project here for enums real quick. And if you just go Google Python enum, it's probably your best bet here. There's an enum module with a class for enum. You can't see the screen. Oh man, it's twice in a row now. Twice in a row. All right, how about now? Can you see the right screen? Okay, without the tiny box. All right, so enums is just a nice way to put a name to a value. So it's essentially a class that inherits from enum, and then we say, hey, here's a name, and I'm going to assign a value. There's no self.attributes, so these are all class level or static variables here. You get a couple cool things by using enum, which is nice. So I'm going to say from enum, import enum. Then if I want to use those enums here, enum is short for enumerable, or enumerate. I think it's enumerable. Enumerations. Enumeration, okay. So if I wanted to have, say, a class for, how about shape names, that will inherit from enum. The only thing I'm going to put in here is a shape name and a value. So I'll say, hey, square is equal to 1, and we'll say triangle equal to 2, and rectangle equals 3. Doesn't seem very useful right now, but what we can do with this is we can restrict certain values here, and then behind the scenes, when you store something in memory, storing an integer value like a 1, a 2, or a 3 takes up a whole lot less space than it does to store the string for square, or the string for triangle, or the string for rectangle, right? Strings take up a lot of space for every character. You need 2 bytes for every character. The way that we store their Unicode values versus just a single integer, we can store in 4 bytes. So it lets us save a little bit of space and be a little more efficient here. And then if I want to ask the user to enter a given shape here, we can ask the user, so we'll have a shape equals an input of a shape. Now, we want to tell them which ones we have here. Right? So we probably can go through, we can say for, now we're going to say, I can loop through these enums here. So I'll have shape in shape names. I think it's loop through. We'll take a look at our example here because I can never remember the right syntax. Okay, there we go, a list of it. And, we can just print list of shape names. Oops, I want to run main here. Let's run this one. So this is not the prettiest printing here, but we can do something and clean it up a little bit nicer here. But you see, shape names, the class, becomes this collection here. When we turn it into a list of, here's square is a 1, here's triangle is a 2, here's rectangle is a 3. So we could loop through each one if we wanted. So for shape in a list of shape names, we can print just shape, Let's see what we get when we print shape. So here are the shape options here. So shape names.square, shape names.triangle, shape names.rectangle here. And if we want to get their values out, we can get either the value or the name of it as we go through. So we have shape, and then if we want to get values out, we do, where is it? Goodness. Where's my better loop here? There we go. Animals in season? Sure. We will just copy paste this, because why not? Nope, that was the wrong. Will this one copy? There we go. And shape names, we'll say shape. We get out the value of it and the name of it here. And look, I'm going to be a good academic here and cite our source. Oops. Should do a pound sign here. I found this online. Here's where I got it from. Right? This is me citing my source. If you want to find something online and cite your source, this is the way to do it. It's easy. You see it right there. Right now, okay, 1 for this, 2 for this, 3 for this. So enter a shape. We can go through and have them pick a value, right, and go through. So when we're using these, then if we wanted to have our shape, then it's our polygon class, right? It has a name. It can also have possibly a type. This is not great here, but that's okay. So we'll default it to 0 for now, I guess. Because if it goes at the end, you have to have a default here, because we have this one that has a default. So we can say myself dot type is the type. But what we could get with that is we could take the particular shape name or shape type. I guess these are types, right? Let's rename this here. So go refactor, rename to shape type. So we'll enter the shape type. And then when we go and make our polygon, we'll take that shape as well. Or if I want to make a specific one, I can say, hey, this one here is a shape type dot, and I can get square or rectangle or triangle. And in my code now, I have a nice name for what this value is. And not quite as useful if we're just asking the user for input, but if I'm using this value in my code a lot of places, now I can say, here's the name of the class, here's this value here, and I can see the nice name of what this value is. And it puts it in a shared spot here, being a class that we can use other places. So when we're doing our alignments, we'll have a class for alignment that inherits from enum, and we can assign us, them, and chaotic. So what that lets you do then is, instead of saying, hey, does their alignment string equal a particular value, right? We could say, hey, if, like in our print polygon here, we could say if my polygon dot type is equal to shape type dot square, right? Then we could go do something. Print is a square. Right? So you can check very easily here, rather than saying, hey, if the type is equal to polygon dot type is equal to square, something like this. And then, when we're comparing strings, what if someone typed it in with the lowercase s? Or in my code, if I had a lowercase s versus an uppercase s, because I typoed it, right? If we use variables here that are fixed, these are constant, right? I can't typo this, because it suggested it for me. And anytime I just pick the value, I know I'm not going to typo it because it typed it for me. So it's safer for us to use as well. So they're handy for use, and then you can use their values if you want in other things. So later on, when we start playing card games and we deal with 2s and 3s and 4s and 5s, right, we can make an enum for the face value of a card. Right, we did our blackjack last semester. So we had to have the value, the face value of the card as 2, 3, 4, 5. We can make enums for, hey, the 2 is value is 2, the 3 is value 3, right, and assign particular values to it, which is fun. So pretty handy. Does this make sense for what we're going to do for alignment then? Mostly we're using it to put a name for it, and then it's more efficient for storage and memory. we'll make our code a little cleaner too when we're checking, hey, because us ships only attack them ships, but Corvette ships, or no, repair ships only repair the same type of ship, the same alignment of ship. So like we're going to be using that alignment a couple places for when we're doing all of our logic. So being able to use, alignment.us or alignment.them or something will be handy. All right, so let me close that one out. Let me go back to GitHub here and add that one in before I forget. All right, so here is enums. All right, then we'll start up a new project for Recursion. 3 Recursion. So the real simple definition for recursion is a function that calls itself. So I don't know, maybe we did. I think we did countdown for n. Instead, if n is less than 0, we're going to print blast off. Less than or equal to 0, right? Because I think at 0 you blast off. If it's not less than or equal to 0, we're going to print n, and then we're going to call countdown of n minus 1. So this function will call itself, changing the value of n. Right? The idea with writing recursive functions is that it's an easy way for us to solve problems that can be broken down into smaller problems. So if we have a big problem that we will call complex, that we don't know what the solution is, well, I can get closer to that solution by taking one step closer, by trying something. So in this case, we're going to take n minus 1. So if we're not less than or equal to 0, we're not solved. We're not done. So let's do something and then try with a simpler step. This n less than or equal to 0 is what's known as a base case. This means if n is less than 0, I know what has to happen. I'm done. There's no further work needed. Right? So it's a known solution, a base case. We're done. So if you're thinking of a problem and you can identify a base case, and you can identify a way to make a complex problem simpler or approach the base case, we might be able to solve it with recursion. Now, recursion is not the answer for everything, but it does make life really easy for us because some things are just naturally recursive in nature. So if you think of your folder structure here, I want to go open this in Explorer here. I've got my C drive, my users folder, my Eric C folder, documents folder, GitHub folder, CIS 2001 folder, week 3 folder. What if I put more folders inside of this folder and put more folders inside of that folder and put more folders inside of that folder? There's no functional way, there is, but it's really annoying to say, hey, keep on opening folders until you stop finding folders, right? So navigating the file system is a very naturally recursive operation. Because you get, here's where I am, here's all the folders inside of this folder, and here's all the files inside of this folder. And then if you want, you can recurse, go to that next folder, do it again, go to the next folder, do it again. So we don't know what the depth is in a given file system. There's probably a limit somewhere in Windows or Mac land, and I just don't know what it is. I don't think we care to find out how many folders you can put inside of folders. That seems like a really bad problem. But that sort of problem lends itself well to recursion. You can do it with non-recursive code or iterative code, but you have to track things, and it's really obnoxious and difficult to do. So any problem that can be solved recursively can be solved without recursion. Sometimes it's just harder. And oftentimes there are better solutions if you're not using recursion, because there is a cost to using recursion. So as we run this here, if I want to just do a countdown, say from 10, here, I'm going to put a breakpoint in and run it with debug mode, and we're going to watch what happens. So right now I'm in my main file at line 8. Right? There is no particular value. I'm going to step into my code here to step into countdown. Now, Python has to remember we were at line 8 to come back here when we're done. But now it knows, okay, we're currently at line 2 of the countdown method here. And we're just going to keep on going here. And keep on going here and keep on going here. So Python has to remember every single time we leave somewhere and call another function. So this is the stack, the call stack. So this was the first call on the call stack. And then it went to here where n was 10. It went to here where n was 9, n was 8, n was 7, 6, 5, 4, right? You can see the value of n. So Python has to be tracking where we left off and what values that particular function had. So we now have 1, 2, 3, 4, 5, 6, 8 copies of n in memory, because Python has to have that somewhere so we can come back to it when we're done. So it's not always an efficient solution to use recursion, but it's very natural, very easy for certain cases. So we need to talk about recursion because we're going to use it later when we start getting to some of our data structures and looking at how we can store data, because some of the ways we store data are more easily worked with using recursion. Because again, if you're dealing with like a list of values, I don't know how many numbers are in there. You're going to give me a bunch of numbers. It could be 5 numbers. It could be 500 numbers. I just need to do something to loop through those values over and over and over and over. So recursion becomes a very easy solution for that. So eventually, these will finish, right? We'll get all the way down to our base case. Here we go. So now n is 0. And now we're going to see these start, well, I'd say they come off the call stack. They're resolved here. And we'll see, okay, this one will be done. And we'll come back to here. 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 We've printed. Oh, it jumped through. Sorry. It didn't let me do one at a time. But all of those would finish. And we can see now we ran our program and we blasted off. Yay. Did anyone watch the Falcon Heavy landing? I saw the video of it. Super cool. I think rockets are neat. I know nothing about them. I just think they're neat. So that's all. All right. So that's our very simple recursive solution here. Now, some other problems. Did we look at the towers of Hanoi? I think we looked at the video, right? Last semester. It's a really good one. So if you look at this Tower of Hanoi animation. So there's a, I don't know, it's not even a legend. What is the, like some story here. Let's just do 5 disks. Get solution. There we go. So, we want 3D. 3D is prettier. The idea here with this Tower of Hanoi is that you can't put a smaller disk underneath a bigger disk, or you can't put a bigger disk on top of a smaller disk. And you need to transfer all 5 of these disks from this peg to this peg. So transferring 5 disks is hard, but what's easier is transferring these 4 disks to this peg, transferring the 5th disk from this peg to this peg, and then transferring the 4 disks from here back on top. That's easier to do, right? Because it's easier to move 4 than it is to move 5. Well, I don't know how to move 4, but I can move these first 3 to this peg, move the 4th one to this peg, and move these 3 back on top of the 4th one, right? That's easier than moving 4. Moving 3 is easier, right? Well, I don't know how to move 3. Okay, well, I can move 2. To move 2, I move the top disk here, the second disk here, and put the top disk back on top of the second. I've moved 2. So we can move 2, right? Then once I've moved 2, I move the 3rd one, and then repeat the move 2 back to here. And then I've moved 3, so now I can move the 4th one, repeat my move 3, which is move 2, and then move 3, and then move 2 again. Right? So in the steps that happen, it's really fun to watch. It does the move 2, then it moves the 3rd one, and repeats the move 2 back on top. Right? Now we've moved 3, so now I can move the 4th one, and then I'll repeat the move 3 to put it on top of 4. Right? Well, to move 3, I have to move 2. Let's move 2, and then I'll move the 3rd, and then I'll move those 2 back. I think the legend is there's some temple with monks somewhere who have to move like 20 of these disks, and when it's done, the world will end, or something like that. I think that was the story here. And you can see this is quite a tedious process here. And if you want to increase the number of disks that you have here, like to 30 of them here, and let's go up to speed factor of, let's just go all the way to 50 because I want to do that. We do 30 disks solution. Didn't let me do it here. Why does it not let me do it? I guess 9 is as much as we get here. Sure. And we show this. It just repeats. So this sort of solution lends itself well to this recursive process where, well, it's hard to move 5, but I can move 4. Well, it's hard to move 4, but I can move 3, right? If I can approach the base case of I know how to do this, and then I just need to repeat. It's kind of fun to watch. Okay, that's probably fine. So the I think they even have, is it tech? No, I thought they had a link for it here. None of that looks fun. This one here. This is pretty much it. This is not code here, but it's close to code, right? So to move from a given node, you have your source peg, you have your destination peg, and you have your intermediate peg. Where's that middle one that we can put it on? Here, right? Find the smallest one, move them, right? Flip it around. There's a better solution here. Where's our Powers of Hanoi Python solution? This is it. The entire code. This is actually really pretty to look at, right? So to move n disks from the source to the destination, with this being our auxiliary here, our extra storage, if we got down to 1, just move the 1. If we're not at 1, well, let's move n minus 1, and we flip the auxiliary to the destination, right? Because if I need to move 5 from peg 1 to peg 2, well, it's moving 4 from peg 1 to peg 3, then moving 5 from 1 to 2, and then moving 4 from 3 back to 2, right? So move n minus 1, move the disk, the nth disk, then repeat the move, right, from the auxiliary we just put it on to where it actually needed to go, here. And that's it. So it works very well with recursion here to move the disks. So if we look up Python non-recursive Power of Hanoi, it's doable, but it's obnoxious. You have to push stuff on, pop stuff off, push stuff on, pop stuff off, and flip things around, and ugh. This is not pretty, right? It's probably more efficient, right, if you look at it. So this one still technically has to store things because you're putting stuff on a stack, so we're still using some memory. We'd have to actually spend a little bit of time looking at the math to see which one is better. But yeah, here we go. Here's the recursive solution. Here's the iterative solution. Definitely we prefer this one, right? It's just easier for us to think about. Okay, so that's a fun one. Now, we're going to take a look at a maze solver. So I think that's a fun way to look at how we can do a recursive function here. So I'm just going to draw a picture here if you don't mind. Now, I didn't bring my tablet. I forgot. I should have brought my tablet here. But imagine we have a maze here, which is just some sort of grid here. Let's just do like 5 by 5. So 1, 2, 3, 4, and 1, 2, 3, 4. And if we wanted to start here and end here. Okay, so imagine it's a maze, and we'll put some walls in. So I'm going to put X's for walls because that's pretty easy. So I'll have an X, we'll have an X, have an X, have an X. So there's a dead end, right? Mazes usually have dead ends because it makes them slightly more interesting. And then we'll put maybe an X here, an X here, and an X here. Now, we can just look at this because humans are pretty talented at this sort of stuff. And we can see there's 2 possible solutions, right? Great, this solution, no problem here. But if we need to dumb this down for the computer, what is the base case when we're in a maze, right? If I'm at any given square in this maze here, right? Because this is row 0, row 1, row 2, row 3, row 4, column 0, column 1, column 2, column 3, column 4, right? For any given location in the maze, what's the base case? How do I know if I'm done or not? Yeah, if we got to the E. If I'm on the E square, I'm done, I win. If I'm not on the E square, what can I do to try and get closer to the E square? I'm sorry? Definitely, we'll have to worry about dead ends in a minute. But before we get to dead ends, if say I'm at here, if I'm at 1, 2, what can I do to get closer to possibly getting to E? What options do we have? We move, right? So we go somewhere. So because we're writing this as an algorithm, it has to have a defined sequence here. So there's basically 4 ways you can move in a maze, right? You can go up, you can go down, you can go left, you can go right. We'll pretend diagonals don't exist. Is that okay? Because that makes it harder. So what should we do first? What do we want to try first? It doesn't matter. Any order will still eventually find a solution, but we just need to pick an order. I'm sorry? Okay, so we'll try right first. What comes after right? What do we try next? Down. Okay, we'll try right. We'll try down. What should we try after that? Left. And then that leaves us with up. So I'm going to start at the starting location. I'm at 0, 0. I'm going to try all of these things. If I can't do it, I just go to the next one. If I can do it, we're going to recurse. And we're going to start again at that new location. So can I go, so we're at 0, 0, right? So we're at 0, 0. We're going to try right, down, left, up. Can we go right from 0, 0? No, there's a wall here. So we can't go right. So right is immediately out. Can we go down from 0, 0? We go down 1. Yes, we can go down 1. So we're going to be at row 1, column 0. We're going to try right, down, left, and up. Can we go right from 1, 1? Right, so we're right here right now. Can we go right? No? All right, so cancel that one out. Can we go down from 1, 0? Sure, let's go down. So now we're going to be at 2, 0. 2, 0. We're going to try right, down, left, and up. Can we go right? Yes, okay, cool. Let's go right. So now we're at 2, 1. Now, these are backwards. Usually the call stack goes the other way, but I didn't want to scroll all the way down for 0, 0. So pretend this is flipped in your head, because in Python, right, we have that call stack. It said I was at this function here. Here's my row, here's my column value. Now I'm at this function here. Here's the new row and column value. So these are getting stacked. I'm just doing it in the wrong order, because sorry. So right, down, left, and up. So at 2, 1, can we go right? Sure, let's go right. Okay. So now we're at 2, 2. We're going to try right, down, left, and up. Sorry, the chicken scratch here is awful, but bear with me. Can we go right? No, we can't go right, so that one's out. Can we go down? Sure, let's go down. So now we're at 3, 2. 3, 2. We're going to try right, down, left, and up. Can we go right? No, okay. Can we go down? Sure, all right, so now we're at 4, 2. Can we go right, down, left, and up? At 4, 2, can we go right? Okay, great. So now we're at 4, 3, or 4, 3. Did I have that wrong? That was 2. That was a 2. This is 4, 3. Okay. Right, down, left, up. Can we go right? Yes. Okay, great. Now we're here. We're at 4, 4. Now the other piece I missed here before we start any of this is, are we at the end? Right? If we got to the base case, just stop. Get out of the maze. Right? If you're not at the base case, then we try these things. Right, down, left, up. Okay, fantastic. So did we get to the end? We did. We went. Right? We found the end. Yay. So we haven't run into the dead end case yet. We will in a minute. So if we tried a different path first, say if we were going to do down first and then try right, and we go down, 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 we get stuck. So what has to happen is we need to undo. So as that call finishes, right, with countdown, right, we got to 0 and we're done. We go back, count n was 1 and then it was 2. We're done here. Right? We need to just go back. So if I were to go down, 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 we would get to 4, 0 and say, I can't go down, I can't go left, I can't go right, can I go up? Now, the problem with that is we were already here. If you go up, then when I call up from 3, 0, it's going to say, can you go down? And you'll say, sure, I can go down to 4, 0. And 4, 0 says, well, I can't go down, I can't go left, I can't go right, can I go up? You say, up, sure, I'm at 3, 0. 4, 0, 3, 0, 4, 0, 3, 0, 4, 0, 3, 0, 4, 0. So we need something to make sure we're not stepping on a square we've already stepped on. So there's something we can do is when you start on a square, you could, I like to imagine them as breadcrumbs. If you remember the story of Hansel and Gretel, leaving breadcrumbs as they walk to find their way back. If we leave a breadcrumb, we'll know, don't go back on that breadcrumb, you've already been here. Bad stuff will happen. Right? We'll just end up in an infinite loop here if you step on a square you've already stepped on. So we can add in a step here that says, okay, are we at the end? Yes. If we're not at the end, put down a breadcrumb. Bread. That's supposed to be a B. Put down a breadcrumb. Then we'll try down, left, up, right, or whatever our algorithm happens to be, so that if I'm checking if I can go somewhere, not only can I not walk into a wall, I can't walk into a breadcrumb. And also, by the way, I can't walk off the edge of the maze here. Right? I can't get less than 0, I can't get more than 4, whatever our maze happens to be here. So this idea is we're going to put these constraints around if I can go somewhere or not. So it should be pretty quick here if we go add a file here. Let's call this our maze solver. So I'm going to write a class for maze solver here because I like using classes. So to create a maze solver, you need to give it a maze to solve, right? And then we can have some of those. We don't even need to use enums all the time because we're only going to use this value internally. I don't really need to use it other places here. So I can say, hey, the start is an S square, the end is an E, a wall is an X, and how about a breadcrumb is, I don't know, how about just a dot or something? We can come up with our own things. But if you give me a maze, so the maze has to be a two-dimensional list, a list of lists, and I'm just going to use characters here because this will make my life easy. And then we'll also have open. Right, is just a space. So I could make a maze if I wanted. Here, I could say my self maze is equal to, so here's my list, and then it'll be a list of lists. So we had start, and then we had a wall, and then we had open, open, and open, right, for that first row. And then we had open and a wall, open, open. I think I put a wall there, right, to make you go around. There's too many spaces there. There we go. And then we were open. This one was open. And then that was open. Need commas. There we go. Commas. Commas. Wow, that tabbed in really funny. All right. Why is it so unhappy? That's weird. That's okay. I'm sorry? Oh, my goodness. Thank you. That's a weird place to put a comma. So it would look something like this. So if you wanted to make a maze, right? This is what we kind of drew here, right, with our walls and our start and our end. So if you wanted to give me a maze, great. Right? If not, we can set our own maze. We'll get to that in a minute. But this way, the maze solver itself can solve or can try to solve any maze you give it here, right? So I'm actually going to keep this here. I'm going to cut this out. We'll just say self maze is equal to the maze you give me. And then over here, we'll make a maze. Because we'll use this here in a minute as our maze. Okay. So the maze solver. And then we're going to have a method for solve. So solve, right, because this is an instance function, right? It belongs to an instance of maze solver. It knows what the self maze is. So I can have 5 different maze solvers in memory, each with their own maze, right? Because we're using a class, we're using instances of that class. This is why these are nice. You don't have to use a class to do this, but I think this makes things a little cleaner for us. And again, we like this object-oriented approach. It's just sort of a nice way to approach things. So to solve then here, well, I need to know where I'm starting. So I can either ask someone to tell me where to start, or I could go find the start position myself. Right? Not all mazes are going to have a start in the top left and an end in the top right or bottom right. No, not every maze is like that. So it probably makes more sense for us to find the start location here. So when I go solve, I need to go find the starting row and starting column. So I can say for row index in range, the length of self maze. Right? So the length of the maze is how many rows it has, because it's a 2-dimensional list. I'm going to range through that, so I'll get 0 up to the number. So this is my row index. And then for every row, I need to look at every column. So for column index, index in range. Now, mazes don't even have to be square. So the better way to check this is to go off the length of the self maze at the row index, right? Get the length of the row that we're currently in, because it could be, a 5 by 10, right? We can make rectangular mazes. They're kind of fun sometimes. Now that I have a row and column index, I'm going to loop through. I can say, hey, if my self maze at the row index at the column index is equal to start, or no, it's a maze solver, not start. Right? If it's my start square, I have my starting location. What do I do now? I need some sort of method that will be the recursive method for me to use here. So I'm going to make another function here. We're going to have a define private method for solve that takes a row index and a column index. So this is, right, we're indicating this is a private function here. You shouldn't use this separately. This is only for use inside the class here, because I don't want the person who's giving me a maze to have to tell me where to start. That's extra work for them. Right? We want to make our code nice and easy to say, give me a maze, I'll solve it for you. Right? Life is good. So if we find it here, we're going to call self.solve given the row index and the column index. Right? This is our start. We'll go find the start location and start our recursive function here. Great. With our solve algorithm, we said we had to do a couple things. First, we're going to check for the base case. So if self.maze at the row index at the column index is equal to mazesolver.end, print, I don't know, you found the exit or winner or solution or something, I don't know, solution, sure, found, why not? And then I'm just going to print self here. There's a fun thing we can do. Remember, you can use this string function. I don't think we talked about it yet this class, but last class, this is how you would represent your instance of this class as a string. So you can put yourself in, I can just say, hey, print, if I want a maze solver, so here's my solver is a maze solver. Given the maze, I could print the solver. Maze, I got to import here, shoot. From maze solver, import maze solver. So without this function here, if I go print it here, I get this. This is not a very useful printed result here. But in Python, remember, everything is an object. Every class implicitly inherits from object. So this is the object's version of string. So you get, hey, here's the name of the class. This is essentially its memory location, best I can recall. Not very good. But if we want to write our own version for how do we define ourselves as a string, great. Now to do this, we can use some of that fancy list interpolation. So I'm going to take a new line character and I'm going to join together something, right? So what list am I joining separated by new lines? Well, I need for the row in self.maze, for row. Oh goodness, row. I need the row for each row in self maze. This is the like one-liner version of looping through a string or looping through a list. These always hurt my head and I mess them up a lot. I just have to Google most of the time. But it's going to take every row one at a time. And what I need to do is I need the string version of that row. Because if you just try and take a row, it's going to say you can't do that because it's not a string. So we need to convert it to a string here. But now if I go and print my maze, we get, oh goodness. Oh, we never returned. Oops, we need to return that. There we go. If we return the value, it should be a little happier. There we go. We get our two-dimensional list back out. And again, it's not the prettiest looking output. We can make this look better. Or we can put in, I don't know, a grid around it or anything we want it to do. But here's a quick little way to output here. Okay. So we can print ourselves out. Now we'll come back to solve here. So we can print ourselves once we found the solution. If we haven't found a solution else, what do we want to do? Well, now we need to put a breadcrumb down, right? Say that we've stepped on the square here. So we're going to take self maze at the row index, at the column index. We're going to assign it the maze solver.breadcrumb. Put a marker down. Don't come back to this spot here, right? Yeah.
So on that picture,
this one?
Yeah, like if you go to the bottom, if you keep going down, when you not feel like come back up to the right.
So what will happen is we want to say that we tried down and it didn't work. We tried down and it didn't work. We tried down and it didn't work. When we come back to 2, 0, we tried down. We still can then try right, left, and up. So just by exhausting all of our possibilities, the recursive nature of this will bring me back to here to try the next step. Yep. So there's not anything we really need to do after that. Okay, so set the breadcrumb. Great. Now, if you want, you can also check to make sure you're not overwriting the start square. I'm not too particular. I don't care if we erase start. It might be nice not to erase. Okay, now I'm feeling bad. So if this does not equal mazesolver.start, then we'll set it to the breadcrumb. Okay. This way we don't overwrite that starting square, just to make this look a little prettier here. Okay. We'll do the breadcrumb. Then we're going to check, hey, if can go right, given the row index and the column index, we will call solve, self.solve. This is self.solve at the row index. Now, when you're moving to the right, row doesn't change, but column changes. We'll change the column index +1. Right? And really, this, if I can go right, if I can go left, I don't know, what do we, can go down. This is workable, and we can write functions to do it, but really all we care about is, can I go somewhere? So I don't need to make these specific to right, down, up. I don't need a different one for right. I don't need a different one for left. I just need, can I go somewhere? And then to go to the right, then I'll take column index +1. Okay, this is right. I was supposed to do down first. Sorry. So down would be row index +1. There we go. Down. And then this one is right. And now you don't want these to be else ifs, right? Because we want to try all of them. We don't say, hey, just because you went down doesn't mean you can't do any of the other ones. So they're all just ifs here. So this is moving to the right. And then we'll go try left. So left would be row column -1, right, to go left. And we'll try up. Up is row -1, row -1. Right? So if I can go that direction, let's go there. Right? So what does this can go look like? This one's pretty quick here. I'm going to define can go given a row index and a column index. So you can either define it in terms of where you can go or where you can't go. I think the can't go is sometimes easier because we need to make sure that we're within bounds first. So we're going to say, hey, if the row index is less than 0, right, or the row index is greater than the length of self-maze, and this is actually greater than or equal to, right, because that is an invalid index. If I have 5 rows, there is no row index 5. You get 0 through 4. So if I'm here, I'm wrong, right? So that's 1. Or my column index is less than 0, or my column index is greater than or equal to the length of self-maze, again, at the row index, right? Because we can be rectangular. I can't just assume I'm a square. So this is also bad, right? So if this is bad or this is bad, I can't go there. I can tell you no. But then I also need to check, okay, just because they're valid, now, is there a wall or a breadcrumb there? Right? So once I've checked that they're valid, then I can say self.maze at the row index, at the column index, and I know I'm within bounds. I won't get a bounds exception, right? Hector, my friend, thanks for donating to the scholarship fund here at the University of Michigan Dearborn College of Engineering and Computer Science. You're a legend, sir. So if this then is equal to mazesolver.wall, that's no good, right? Or if it equals a breadcrumb. right? I need the slashes here, right? Sometimes it adds them for me and sometimes it doesn't. I never can remember why. No? Not like that one? Need more parentheses? What do I need here? Oh, it's because this is an if here. Yep, sorry. So if any of that is true, right, I'm going to return false. Because that was no good. You cannot go there, right? If you're just checking if something's true and returning that, and otherwise returning the opposite result, we don't need an if here. We can just return. And then really we want all of this then, and we want not that. So if any of this is true, it is no good. I want not good to say you can't go there. This gets a little awkward. You also could rewrite this to say, hey, it is within bounds, and it's not a wall, and it's not a breadcrumb. And you can use ands instead of ors. This is purely just whatever style preference you like here, whatever makes the most sense to you. Any combination will work, right, as long as we do it appropriately. Right? So I'm saying this is bad, or this is bad, or this is bad, or this is bad. You could say this is good, and this is good, and this is good, and this is good. You get the same result. Right? So either way, either should be fine. But now we have our can go function, right? So what, it doesn't like all my extra spaces? Oh my goodness. These yellow lines drive me nuts here. I'm sorry. Do we not need them now? Slashes? All right, we don't need the slashes. Or. I don't know why. Under indented for visual indent. Okay, this is where PyCharm likes it. That's fine. Sorry, just want to get rid of the yellow lines. They're just, they don't hurt anything, they just bother me. I'm sorry. All right, so can go right, can go down, or no, we're going to try down, right, left, up, and try it. If we get to the end, we're done. Right, we'll print ourselves. Should we try it? Give it a shot. We need to run this one here, right? No, I never called solve. Oops, so we need to call solver.solve, right, to actually run the method. Let's try that. And we get 2 solutions found. Look at that. Right? We get this solution where we went, found the dead end, came back, tried down and to the right, we found one. Then after this one came back, right, we came back to this location. We said, okay, we tried down, we tried right, how about up? And it goes and follows the up path to find the other solution. So it can find more than one. Right? If you want it to stop as soon as it finds a solution, we need to add a little more logic here. Right? So instead of just saying, hey, am I at the end here? We can add in another value here. So self.solve we'll say is false. So then if we find a solution, we'll say self.solved is true. And then else if self.solved, elif not solved. So if we solved it, set the solved Boolean. Yes, we've solved it. Then the rest of our check here can say, okay, if we're not solved, let's keep on going. If we're not solved, keep on going. So as soon as we find a solution now, we'll bail. We'll say we're done. We found one solution. Nothing else gets attempted because we're done. The next time we go to that recursive call to solve, we come back here, it's going to say, oh, you found a solution. You're solved already. You don't need to try going up. Now, the downside here is that if we were to change the order of the steps here, if we were to try up first here and run it, the first solution it finds is not the best solution. Right? This is a very naive approach. This is called backtracking. It's a recursive backtracking. It just tries something, and if it gets stuck, it backtracks, steps back, undoes it, tries it again. So we're not always going to find the best solution if we bail early. So that is, one of the nice things. If we find every possible solution, we can then see maybe which one was best. Now, one of the classic things you look at when you start studying AI is pathfinding. I don't know why, but pathfinding is a big thing, and there's cool algorithms for finding paths for things. Recursive backtracking is not a good solution for finding a path. Right? It's very inefficient. There are much better ways that very smart people have come up with. But this one is simple, and it illustrates this recursive idea for us. Right? I'm going to try something. If I reach the base case, great. If I didn't reach the base case, get closer. So the other piece here is that we really have kind of more than one base case here, right? Because once we hit a dead end, like if there's nothing for us to do, we can't get any closer to a solution. That's when we undo. That's when we backtrack here. So it works out for us. So if we wanted to, we could add in some other stuff to mark dead ends rather than just leaving breadcrumbs. Again, it's a small, a couple changes to do. But if you wanted to say, hey, this is a dead end, don't go here, to mark it distinct from it's just a breadcrumb, we could do something like that if we wanted. There's additional things we can check. So when we come back on Thursday, we'll look at a couple other things we can do with recursion to undo changes that we made. Because you might not want to leave the maze changed. Maybe we want to find the path and then undo all the changes we made to the maze to put it back in a state that it used to be. We got some fun options for that. So how you feeling so far? Doing okay? So you have to be able to identify a base case, a known solution. You have to be able to make the complex problem simpler to approach the base case. Then we might be able to solve it with recursion. It's not even a guarantee at that point. You probably can, but it's not a guarantee. Right? If we can do those things, great. We can make our recursive solution. The method function calls itself. Now, this is a nice, pretty method here, this function for solve. Solve is recursive because it uses the private solve that keep getting called and called and called and called and called. This is a common way of, I want to make my code easy for people to use. When we think about object-oriented programming, we think of the public functions we give people. We want to make them easy. You don't need to tell me where the start is because I'll go find it, right? That sort of thing. So we make life easy for folks if we use these private helper recursive calls. Cool. So I think that's about as far as we wanted to get today. We being me, I'm sorry. I think I'm royalty, I guess. So Eric in Norse? I think it's Norse, right? Of name Eric. Scandinavian. Oh yeah, Norse. Okay, look at that. I know a couple things. Is ruler, so technically I am royalty, just in name only though. So, all right. So let me commit this here. So this is our maze solver here, and then we can call it a day. We'll meet up on Thursday. And now that I finished talking about enums, I'll post the chapter quiz for object-oriented programming. We'll have a whole week to do it. It's open book, open notes. You can look at the questions, close it, come back to it anytime you want here. These are basically free points for you if you go and open your textbook. Right? Just please go and do the reading. Right? As much as I like to imagine, I give great examples. You want to see it more than once. You want to hear it more than once. Right? The more we're interacting with these topics, the better it's going to sink in for you. So I'll do some examples. You can read the book, try the book examples if you want here, take the quiz, make sure you picked up some of that from the book here. It'll help solidify it for you, but they should be free points from there. So if the questions aren't clear, it's because I wrote them and it made sense in my head. So just ask in the Discord, send me an email, text me like, hey, I don't know what you're asking in this question. It makes no sense because I probably just screwed up writing it. Okay, so we'll have the whole week to do it. It'll be due like next week, probably 11:59 p.m. or something. Like I don't want lots of time pressure on these. Yeah. So it's open it as long as you get it in by the due date. You're great. So usually I'll post them after we've talked about the chapter. It would have been Thursday, but we didn't actually finish everything. I still wasn't feeling great Thursday. So finally getting back to closer to normal. All right, folks, you take care, and I will see you Thursday.